Hello students, let us start with the last lecture of module 5, that is battery efficiency calculations. So here we are going to deal with the battery efficiency. We all know that when we talk about efficiency, we are talking about output to input ratio. How much input we have given to the system and how much output we are receiving from the system. Here the system is our battery. So in the case of battery, we define two types of efficiencies. First is the ampere hour efficiency and the other is our watt hour efficiency. So we'll discuss briefly about both the efficiencies. The first is the ampere hour efficiency. We know that ampere is the unit of current and hour is the unit of time. So what we are doing basically here is we are multiplying current and time. We have learnt in basic physics that charge Q is responsible for the current, and we all know the formula that current I is given as the rate of flow of charge, that is dq by dt. So what we are doing here is we are multiplying dq by dt with a time interval. Therefore, what we will get is charge. So in the first efficiency, we will have the ratio of the output charge divided by the input charge. Output means how much charge the battery can supply to a load, and to do so, how much charge it requires to charge itself. Next is the watt hour efficiency. Now we all know that watt is the unit of power and we are multiplying it by time. So we will receive a quantity that is energy, because power is defined as the rate of change of energy. Therefore, power into time will give us the energy efficiency. So in this case, for a battery, we are talking about the ratio of output energy by input energy. How much energy the battery can supply to a load divided by how much energy we require to charge the battery. So we look at the definitions of the charge efficiency or ampere hour efficiency. It is defined as the ratio of total charge supplied by the battery to the total charge stored in the battery during the charging period. So if ID is the amount of current which the battery can supply, and if it supplies this current for TD duration of time, then ID into TD gives us the amount of charge which the battery can deliver to the load. Similarly, IC is the charging current and TC is the charging time. When we multiply these two, we will get how much charge we have stored in the battery during the charging period. So here we are dealing with a ratio, that is QD by QC. Next is our watt hour efficiency. So here we will be multiplying the output power, that is the power given by the battery to the load, into the discharge time. This will give us the total energy supplied by the battery divided by the power input, how much power we have used in charging the battery, into the charging time will give us the total energy supplied to the battery for charging. So we all know that in DC, the power in an electric system is voltage and current multiplied. So VD is the terminal voltage of the battery during discharge time, and ID is the amount of current supplied by the battery. If you multiply it by the duration of time during which the load is connected across the battery, then we will have energy delivered by the battery in the numerator, and in the denominator we have the terminal voltage of the battery during the charging. Of course, we have to charge the battery at a higher voltage than the terminal voltage. So VC is the amount of voltage that we are supplying into the current drawn by the battery during the charging. So VC into IC will give us the power input to the battery, and when we multiply it by the time of charging, it gives us the energy. So it is written as NWH, watt hour. The earlier efficiency was written as eta AH, ampere hour. Now we can clearly see that the two ratios have some terms in common, and therefore we can establish a relation between the ampere hour efficiency and watt hour efficiency. So this is the relation between ampere hour and watt hour efficiency. Here watt hour efficiency is VD into ID into TD, and ID into TD divided by IC into TC gives us the ampere hour efficiency. Therefore, if we separate this VD by VC, the rest of the terms give us the ampere hour efficiency. So watt hour efficiency is equal to VD by VC into eta AH. So this is the relation between ampere hour and watt hour efficiency. Now let us move on to some numerical problems. So here we have our first problem, that is, the question states a battery has taken a charging current of 5.2 ampere. It means that IC, the charging current, is 5.2 ampere for 24 hours. This means that this is the charging time at a voltage of 2.25 volt. It means that this is the charging voltage. The next part of the question is, while discharging, it gives a current of 4.5 ampere, which means that 4.5 ampere is the discharge current, ID. For 24 hours, it is being discharged, therefore, it is TD at an average voltage of 1.85 volt, which means that this is the discharge voltage. So what we are required to calculate? We need to calculate the quantity efficiency and the energy efficiency of the battery. So we know that the ampere hour efficiency is called the quantity efficiency of the battery, and it is given as ID into TD divided by IC into TC into 100. So when we put these values, ID is 4.5 ampere, 4.5 ampere into TD, discharge time, that is 24 hours, divided by IC is 5 the charging current is 5.2 ampere multiplied by the charging time, that is also 24 hour, into 100. So if you calculate this, this comes out to be 86.54%. This is the quantity efficiency. The next part of the question asks us to calculate the watt hour efficiency or the energy efficiency. So we know the formula for this. This is VD into ID into TD divided by VC into IC into TC into 100. Alternately, you can also use this formula. You have already calculated the value of TD ID by ICTC in the above expression. You can use it into 100. You can use this value here. So it comes out to be 86.54 into VD by VC. VD is 1.85. 1.85 divided by VC, that is 2.25. Now this comes out to be approximately 71.15%. So this is the solution for the first example. Now here you can see two things, that is the ampere hour efficiency is 86.54 and the watt hour efficiency or the energy efficiency is 71.15. It means that the value of eta AH is greater than the value of eta WH. So we will look into this matter, why this efficiency, watt hour efficiency is less than the ampere hour efficiency. So this is the question, why ampere hour efficiency is greater than watt hour efficiency. The basic reason behind this is, when we are calculating the ampere hour efficiency, we are talking about the charges. We are talking about the charges. So the amount of charge stored inside the battery, suppose this is the battery, the amount of charge stored inside this battery according to the laws of KCL will be conserved. There may be some leakage current flowing from one terminal to the other due to faulty insulation or some circulating current inside the electrolyte, but more or less the amount of charge stored on the positive plate of the battery, that will be delivered through the load, through the terminals and back to the negative plate of the battery. But when we are considering the watt hour efficiency, we are also considering the internal resistance of the battery. So this is the internal resistance of the battery and this is the load resistance of the battery. So if this is the ideal battery, This is the internal resistance of the battery and this is the load resistance of the battery. And this is the current flowing through this circuit. We all know that the internal resistance of the battery is always connected in series with the battery and the load resistance. Therefore, some amount of I square R losses will be occurring here in the internal resistance when the current flows through the battery. This internal resistance was not considered while calculating the ampere hour efficiency. That is why the ampere hour efficiency comes out to be slightly higher than the watt hour efficiency. Now moving on to the next question. The question states an alkaline cell is discharged at a steady current of 4 ampere, which means that the discharge current is 4 ampere and the discharge time is 12 hours. So TD is 12 hours. The average terminal voltage being 1.2 volt. So 1.2 volt is your VD, the discharge terminal voltage. Now the battery has already been discharged. Now we have to charge it back to the original state. So to restore it to the original state of voltage, it means that we are charging the battery back to its initial stage. That is the charged state. A steady state current of 3 ampere. So 3 ampere is your charging current and this is a constant current, steady current. This is the charging current of 3 ampere and it is being charged for 20 hours. TC is the charging duration is required. Average terminal voltage being 1.44 volt. It means that 1.44 is the VC, charging voltage. The question asks us to calculate the ampere hour and watt hour efficiencies. It is similar to the last question. It is eta AH. Ampere hour efficiency, we know it is IT into VTD divided by IC into TC. You can put the values and solve for this efficiency and it comes out to be 80%. And next is the watt hour efficiency. So you can use eta AH here. So eta AH into VD by VC. You can put the values and calculate the efficiency. This is a simple example just like the previous one. So it comes out to be 66.7%. Now we move on to the next question. Now this is a tricky question. You have to first understand what the total question is asking. So it starts with 35 lead acid secondary cells, each of discharge capacity 120 ampere hour. So here the term 35 cells. So these secondary cells, if you remember the definition of battery, a battery is a combination of the series combination of cells. It's the series combination of individual cells. So here we have 35 individual cells which are joined together to form a battery. The other data are given. 120 ampere hour is the discharge capacity, 12 hours is the discharge time, are to be fully charged. All these 35 series connected cells are to be fully charged at constant current for 10 hours. The current here is not given, so we will have to calculate the current. The DC supply voltage is 125 volt, which means that a 125 volt DC supply is to be used to charge these 35 cells. The ampere hour efficiency is 80%, and the EMF of each cell at the start and at the end of the charging is 1.9 volt and 2.6 volt respectively. Now we are required to calculate the maximum and minimum values of external resistance necessary, and we have to neglect the internal resistance of the cells. Now we have two cases over here. So case 1 says that these 35 cells are connected in series. These 35 cells, this is a combination of 35 cells. These are altogether 35 cells. These are connected in series and they are being charged by a 125 volt DC supply using a limiting current resistor. So we have a resistor over here which is limiting the charging current, because we need to have a constant charging current for 10 hours. So this is a 125 volt battery. The 125 volt DC supply which is being used to charge these 35 cells. Now another data has been given over here, that each cell at the start of the charging has a voltage of 1.9 volt. So we have 1.9 volt across each of the cells. Across each of the cells. What will be the total voltage across this branch? We are calculating the total voltage across this branch. We call this VB1. It is easy to calculate. VB1, that is 1.9 into 35. This comes out to be 66.5 volt. Now we can see that when this is at case 1, the starting of the charging stage, the voltage across the branch of cells or the battery is 66.5 volt, and we have 1.9 volt across each of the cells. And at the end of the charging, the data has been provided that at the end of the charging the voltage rises to 2.6 volt, which means that at the second case this voltage, VB voltage, will be somewhat higher than VB1. So if we are using a 125 volt DC supply for charging the batteries, in case 1 the value of resistance R1 has to be greater, because the opposing voltage here VB1 is smaller, and at the end of the charging period, when the battery terminal voltage rises to 2.6 per cell, the opposing voltage will be somewhat smaller. Therefore, we will require a lower value of the external resistance. But in both the cases, the charging current has to be same or constant. Suppose we take the charging current as IC. In the second case, we have the same set of cells. Again, we have 35 cells, and we have the same supply voltage, that is 125 volt DC. But now the value of resistance has to be changed to have the same charging current IC. So again, we have got 35 cells over here connected in series, but the voltage across each of the cell is now 2.6 volt. So what will be the total voltage across this battery? Suppose we call it as VB2. This will be 3.35 into 2.6. That is equal to 91 volt. Now we will have to have a different resistance R2, which will control the charging current IC, because the supply voltage is constant, that is 125 volt. Now we will move on with the calculations. Now the discharging ampere hour given in the question. So the discharging ampere hour is given to be 120 ampere hour, and the ampere hour efficiency is given to be 80%, or you can use 0.8. Now what should be the input ampere hour for charging? We need to calculate the input ampere hour. Remember that the ampere hour efficiency is 80% and the discharging ampere hour is 120 ampere hour. So obviously we need a higher ampere hour for the charging. So the input ampere hour will be discharging ampere hour. The discharging ampere hour divided by the ampere hour efficiency, that is 120 divided by 0.8, which gives us, you can calculate it, it comes out to be 150 ampere hour. Now the charging time given in the question is 10 hours. Therefore, the charging current should be the input ampere hour, that is the input 150 Ah divided by the time of charging, which means that we will have 150 ampere hour divided by 10 hours, that is 15 ampere. So actually we require 15 ampere charging current. Now for case 1 that we had discussed, we should have maximum resistance in the external circuit because VB1 was less. So R max will be equal to the total potential difference across the circuit, that is 125 volt, that is the DC supply voltage, minus the voltage across the battery at the start of the charging period, that is VB1 that we have calculated, divided by the charging current IC. So VB1 was 66.5 volt. So you can put the value of VB1 as 66.5, and you can place the value of IC, that is 15 ampere. Therefore you will have a resistance of 3.9 ohm to be connected in the external circuit. Next we move on to case 2, where the minimum external resistance has to be connected. We are using the same expression, that is 125 minus VB2 divided by the charging current IC. IC will remain same, that is 15 ampere. VB2 we had just now calculated as 91 volt. So if we place these values, we will have a resistance of something around 2.27 ohm. So this was all that was asked in the question. Moving on to the next question. The question states a discharged battery is put on charge at 5 ampere for 3.5 hours at a mean charge voltage of 13.5 volt. So this is the charging current IC, 5 ampere. The charging time is 3.5 hour and the charging voltage VC is 13.5 volt. The second part of the question is, it is then discharged in 6 hours. It means that discharge time TD is 6 hours at a constant terminal voltage of 12 volt. 12 volt is the discharge voltage VD through a resistance of R ohms. Now we are required to calculate the value of this resistance R for an ampere hour efficiency of 85%. And in the next part, we are required to calculate the watt hour efficiency of the battery. Now we will use the expression ampere hour efficiency has been given as 85%. So ampere hour efficiency is ID into TD divided by IC into TC. IC into TC. All the data has been given. We are required to find out the discharge current. Eta AH has been given as 85. the discharge time has been given as 6 hours, the charging time has been given as 3.5 hours, and the charging current has been given as 5 ampere. So all we are required to calculate initially is ID. So we can rearrange this equation and we will have eta AH into IC into TC divided by TD, and we can place the values. Eta AH is 85%, or we can use 0.85 into the charging current has been given as 5 ampere, so we will use 5. The charging time is 3.5 hours, that is 3.5 hours, and the discharge time has been given as 6 hours, so we will use 6 over here. So here we can calculate the discharge current as 2.48 ampere. Now for this battery, which is giving a 12 volt supply to the load, what should be the value of resistance R? This is simple to solve. We are using the relation V is equal to IR, and therefore the resistance value R should be equal to VD by IT. That is 12 volt divided by 2.48 ampere. 2.48 ampere. This gives us to be 4.84 ohm. The next part of the question, which requires us to calculate the watt hour efficiency. We can use the expression eta AH into VD by VC. Now the eta AH has been given as 85%, VD has been given as a 12 volt, and VC has been given as 13.5 volt. So we can put the values and calculate the efficiency as 75.55%. So this was all in efficiency of batteries and its calculations. You practice these questions, and most probably the questions asked in the semester exam will be somewhat like this. Maybe the values will be different, but the pattern should be the same. Only you have to remember is the formula. Thank you.